You can start with.
Okay, sir. On behalf of Department of Civil Engineering, College of Engineering, Kidangoor, I welcome you all to the second session today. Our expert for this session is Dr. Bino I. Koshi, sir. Dr. Bino I. Koshi, sir, completed his B.Tech degree from TKM College of Engineering in 1985, M.Tech degree from IIT Madras on a Gates Scholarship in 1987, and PhD from IIT Madras in 2007. He retired from government service in April 2019 and currently working as professor in Civil Engineering Department at Amaljodi Engineering College, Kanjirapalli. In between 2005 and 2016, he served 7 years as the head of Department of Civil Engineering in Rajiv Gandhi Institute of Technology, Kottayam, in two separate terms. While serving as the head of the department, he started a PG program in transportation engineering in 2011 at RIT. His teaching and research interests are travel demand modeling, transportation planning, traffic engineering, road safety, and ITS. He has guided 39 postgraduate dissertations. Currently, he is guiding 2 PhD scholars. He is the recipient of Best Teacher Award by Alumni Association of RIT. He has published 34 papers in international national journals conferences. He has successfully completed many projects sponsored by AICTE, TRC. He was the coordinator of Techie project of RIT. He is a fellow of Institution of Engineers India, life member in Indian Road Congress, Indian Society for Technical Education, Institute of Urban Transport, and Indian Concrete Institute. He is a honorary member of Builders Association of India. I wholeheartedly welcome you, sir, to deliver the session.
Thank you and good morning, all of you.
Good morning.
Thank you. Thank you, Bindia and Professor Matthew, for inviting me to this FDP program at College of Kidangoor. I understand that this is a program which probably covers a wide variety of topics in civil engineering, advances in various fields, and I am supposed to talk to you on advances in traffic engineering and management. Maybe some of the deliberation which I'm going to do may be known to you already, but I'll take you to some of the advances which are happening now in the field of traffic engineering as well as data analysis and management. If any time you would like to interrupt me if there is a lack of audio or problem with my presentation, please interrupt the. I request you to interrupt me. Okay. Fine. Traffic engineering, if you look at traffic or transportation engineering, it's actually a key indicator of how the standard of living is. So every country which is developed has very good transportation. That is an indication of the high standard of living. But when you look at transportation per se, you can see there are a lot of issues which are connected with this particular mode, especially a lot of accidents and fatalities. Then in many countries, there is increasing parking difficulty. Road spaces are not sufficient, so that will result in congestion and delay. So delay is one of the big issues in many of the cities in India, because we know that people often tell about how much time they take to travel rather than how long they have to travel. Okay, that is the way people perceive the travel time and the time to reach the destination. So to reduce the negative impact, now we have to collect data, then we have to analyze it and understand where the problem is. If it is specific to a location, now we should be able to pinpoint to that location and then suggest some remedial measures. So this is why as we progress, the transportation engineering or traffic engineering has to address how efficiently you manage system rather than providing something new. Okay. We will be talking more on traffic surveys and studies as we progress. Now, what is the requirement as far as a good traffic engineering or system is all about? One is efficiency. Now, efficiency means when you have a road system, we have to see that how the road system is managed efficiently. So that probably is an integration of the already provided infrastructure and how well the traffic is managed on that. So that is what efficiency is all about. Now, if you probably have a signal system on a road network, so how well you can integrate these signals, or how we can coordinate the signal so that there is an efficient movement of the vehicles. So that is again, if you need to have a system, there should be a seamless connection between one mode to another. That means the people should be able to switch mode and go on to different modes as they choose, from a personalized mode to public mode, and then probably a green mode, something like bicycle or walk mode or whatever. Okay. Then efficiency also looks in from the perspective of technology. Now, as we progress in technology, that means we can have some system developed to increase its efficiency. For example, if you have a signal system in a city, by integrating all this and seeing how the traffic moves in a corridor, and how long does it take to reach from one point to another, we can redesign the timings, and it may be adjusted to adapt to the changing needs at a point of time. So that is what technology is all about. Or suppose you have an incident at some place. For example, a minor accident takes place, and there is a lot of backlog in that particular stretch. And once you identify that, there should be a system in place to divert the vehicles to other links. So that is what technology is all about. Then comes the land use and resource controlling. So traffic is actually, or the trip which you make is actually a derived demand. So there is some need for a travel or a trip which you make. So if you can control the land use, we can probably control how much people are there on the system at a point of time. So this also calls for efficiency. So it's a total integrated planning approach in which there is the existing system, there is integration of technology, and also how well the land use used is what is going to control efficiency. Then about quality. So quality is to ensure that the negative impact of traffic is reduced. And once you reduce the negative impact, you can also that the system will have less pollution or less impact on the environment. So there are places, many places where you can see if it is the timing of the signal is not well designed, or the intersection is not well designed, that will lead to more and more of pollution at that particular point. So we have to ensure that minimum time of waiting is involved at an intersection so that the quality can be improved and the pollution can be reduced. And the last requirement as far as we're concerned is equity. So what do you mean by equity? That is to meet the travel demand of all communities. That means there should be equitable travel options to all sections. That need not be personalized mode of transport. You can have public modes itself with various cost of travel that will suit your income so that they can select and still your travel need is completed. So these are requirements as far as traffic is concerned. Then we come to transportation studies. This is actually an overview of what all we do. That is, we may do origin destination study. That is part of the planning process to understand where from people originate or travel and to where they would like to go. So once you have this information, you can probably think of new connections between those pairs of OD, and you can open the facility which are available. Then the traffic volume study, which is very extensively being used these days, not only to find whether the capacity is available. We can also find if there is a seasonal variation in the demand, if there is an incident. So what will happen if there are what you call this is the stretch is not maintained or modified. So all this can be found out by proper traffic volume study. Then comes the spot speed study. That means at specified locations at a point of time, we may find out speeds which are indication of the quality of the travel or quality of the traffic. So spot speed is essentially the speed of the vehicle estimated at a particular instant. So that is indication of how fast the vehicle is moving. So we can probably connect that with the level of service as well. So that is also again connect the traffic volume. So that is also a possibility in the transportation study. Then comes the travel time and delay studies. Now all of us these days use computer based or what do you call it, route navigations and guidance. And that particular assistant will tell you how much time is going to take for you to reach the destination. So how the travel time is estimated realistically? That's the question. So is there any parameters which can be tweaked or modified so that we get a better estimate of the travel time? Or is it just by connecting the what you call it, the mobile data and over the Google network, how long or how fast they move is an indication of real travel time? If that facility is not available, how do you estimate the travel time? That's the question. So how much delay is involved in a particular intersection? So what is the total delay at the intersection? So all this is studied by travel time and delay studies. Then parking studies. So we ignore certain aspects in our real life. That means the moment you purchase a car, the car will have a certain footprint. Either that car will be in your house, or the car will be on a street, or it will be moving. So when you reach your workplace, you leave the car at that place and go to your work spot. So wherever you are, the moment you purchase a car, that means there has to be a space where this can be parked or can be allowed to move. So that is the what you call it, importance of parking studies. So parking is a very important study as far as city planning is concerned. The urban what you call it, the quality is concerned. Okay. Then the route guidance and real-time applications. So this is where I told you when there is an incident in some what you call it link. So how well you mitigate that and how will you anticipate this problem and how we can dissipate the congestion at a particular segment by distributing this particular traffic to other legs or other links. Again, about incident mitigation and detection. Now, if you look at the category of studies, why it is required, we can broadly, I can say there are 4 different purposes. One is to have inventory. Second is to have administrative details or studies. Third is to have dynamic studies. And of late, we do a lot of forensic study as well. So inventory, basically, it's a collection of how much street you have, what are the street transit routes, what are the regulations in place, and parking, whether it's off street or on street. All these are your basic inventory. Then when you look at administrative study, that is use of existing records to prepare inventory that is relevant or which might also help you in planning further or your administrative purposes. Like for example, if you would like to place some control over a certain category of vehicles, so we may do a study which probably will give you an idea about how much that particular type of vehicles are present in the road. Okay, that may be due to an administrative reasons. And third could be the dynamic studies that involves data under operational conditions. So this is the real time feel of what happens on the road or the street. So that is speed, traffic volume, travel time, the delay involved, parking and accidents. All those are a multifaceted or what do you call it, detailed study which is going to throw light into how the traffic is going to behave. And lastly, there is a lot of important forensic studies as well. That is basically post-crash scenarios and crime investigations. So in the crime investigation itself, we may probably look for violations, if any, identification of vehicles, the type, the numbers, or if it is possible, the speed at which it was moving at the time of accidents, or if it meets with a fatal accidents or something. So this is again for different purposes. So it's not inventory, it's not administrative, it's actually for the law enforcement agencies as well as legal aspects. Now, if you look at this particular picture, you know that this is what India is at this present day. So highly heterogeneous traffic. This is not so heterogeneous as in many of the cities. We probably can see cars, auto rickshaws, and two-wheelers, but there could be 5 or 6 different types of vehicles at any point of time on a road. That is going to make our job difficult as far as Indian traffic engineers are concerned. So in addition to that, there could be presence of animals and pedestrians on the road. So each and every vehicle will have a different operating characteristics, different speed possibilities, or acceleration or deceleration and braking efficiencies. So imagine that you have a system where you have different types of vehicles, the different type of operational capabilities, and operated by different individuals or human beings. So we can imagine how complex our traffic engineering or data collection and analysis would be in our scenario. So we may do traffic volume and classification, but the challenges are much more, which you don't anticipate in any of the homogeneous traffic conditions in developed countries. Now, where do we apply this traffic data? One is to design road and its improvement. Second is study of intersections. Then study of traffic control systems like signals and coordinate signals and things like that. Traffic forecast and predictions. Then study of accidents. Then if you do a highway project, the cost benefit analysis. So for all this you need traffic data. Now I'm not going to talk more on spot speed study because all of us might have heard about what speed is. How do you estimate speed? Speed is nothing but the time taken for a vehicle to travel a small base length where the vehicle is not expected to change its speed. That means you assume that the speed remains same or that particular length, or you can probably use a radar speed gun where the Doppler effect or the sound is used. The incident sound and the reflected sound are collected, and then we can estimate that as a speed estimate. That is a very clear estimate of what happens after a modification is done. If the road is modified, the stretch is relayed with a new surface, or the geometry is changed, you can have a before and after study. So one of the best methods is to find out the spot speed and compare and find out whether your intervention has been successful or not. Now, these days you don't go to the field and do it. You probably do it on a continuous basis. One of the challenge in the identification of vehicle as well as speed estimation is that of the background information and noise or lighting conditions. So we have come up with a new technology where you have dual camera systems in which you may expose the vehicles and find the time which it takes to travel a particular length, and this time may be computed to have the speed estimate. Okay. Now, when you look at a highway or an urban road, this is actually a homogeneous traffic situation where most of the vehicles are cars. Now, this calls for identification of multiple number of vehicles at a time. So some company has come up with 32 vehicles to be identified and tracked, and the speed is estimated along with this license plate if possibility is there. So a cordon system is a very beautiful arrangement by which you can have multiple vehicles, speed can be estimated. So it has got a radar unit, it has got an advanced resolution camera, and license plate recognition system is there. And you can see that the camera is mounted above a gantry, and the vehicles are, when it comes to the field, you can identify the vehicles, and then the speed can be estimated depending on the the conditions in the background. Now, another challenging proposition is to have the volume count. So volume count, as you know, people sit by the side of the road and they have a sheet of paper on which they record. So obviously, when the traffic is very lean, when the traffic is very low, it's very simple. And when the traffic is continuous and on a highway, it is easier and cost effective to have this sensor tubes or cables across, so that when the axle cross on that is actually taken as an incident, and that is made as a count. So these wires which are seen on the second figure is actually not actually classifying the vehicle if it's not connected with the weigh in motion. So weigh in motion is actually to weigh the weight of the vehicle. So that is indirectly converted that as a classification. Okay. But when it comes to intersection, this intersection looks a beautiful one if you are not going to follow the trajectory of each and every individual vehicle. Now imagine that you sit at an intersection and try to manually track the movement. So you'll be having a lot of confusion as to how this can be recorded. So in this particular scenario, human intervention or human counting is not going to help us if you don't switch to computer-based vision and analytics. Now, as you know that volume counts, in fact, are now numbers, the moments, classification at any point of time at a location. Now, this data which you collect, it is actually to find or identify the critical flow time periods. So, like for example, when it's a peak, whether the morning peak and evening peak are similar, whether there's a seasonal variation in the demand, whether a particular festive season has some effect on the traffic demand, whether on Monday and Friday the traffic are same or compared with the weekly traffic demand. So all this information can be obtained by conducting traffic volume counts. Okay. Now also you can find out the composition of large vehicles or the effect of traffic due to the presence of large size vehicles. Now, India is actually going fast pace. We have better and better road network. So when you have better road network, you have larger and larger vehicles, especially goods vehicles are going to ply on the roads. Now we may be able to concentrate and find out what is the effect of those in the traffic operations. And the next line, when you look, you can see that in 2017, one of the study has shown that world over, there are 500 millions of cameras. And if you look at the volume of images which they capture, it is phenomenal. It is to the tune of 15 billion gigabytes of data every week. And that keeps on piling, and we don't know what to do with that. And if you want to go back to this data and find out what is the trend in that, or if you want to find out what has really happened at a particular day, it is very difficult without the machine interventions. So that is why, these days the latest publication has shown that there is an artificial intelligence methodology for analytics of traffic data, so that the freeway traffic management can be better controlled or better managed. So AI techniques are actually to find patterns, find incidents, find how this incident has happened, and that can be reflected, whether this is going to form as an incident or a traffic delay or whatever. So if you have an idea about how it is going to progress, probably you can forewarn and take a preventive measure. That is what the AI techniques and machine learning techniques are going to help us. Now, one of the practical application which has been developed is by the SBIR, that is the Small Business Innovation Research and Small Business Technology Transfer of USA. has funded one particular program in which there is an artificial intelligence-based traffic data analysis tool. This tool or the analysis will be now integrated with the signaling operating system, or they call it as SOES in a particular location. So traffic signal operation analysis expert system. Now that may be modified with the AI and machine learning tools, so that you can have the multi-source big data, which is actually going to help you to identify the incidents and it what you call it, management. Okay. Now, if you want, if you have the real-time data, and if somebody can tell the traffic manager this is going to happen in so much time, if you don't control this traffic at this point of time, that is going to help you in a long way. So this is the advantage of an artificial intelligence traffic data analysis tool. Now we move on to traffic or vehicle classification. So classification of vehicle could be used for structural and geometric design, for computing the highway user revenue, especially toll. How much toll would you get? And also to compute the capacity. Okay, and also, and then to find whether there is a what you call it, a reasonably high probability to believe that a particular type of vehicle is going to affect the crash. For example, the truck versus two-wheelers, a truck versus pedestrians. So pedestrian crossings and accidents. So all this can be studied if you have the vehicle classification with you. Now, users also, you know, that payment design, payment management, how to resurface or what is the schedule of resurfacing, planning for commodity flows and freight management of movement. That's very important because time is money as far as the freight and commodity flow is concerned. Then you may also find the development of weight enforcement strategies. Now, as I told you, the payments are now designed for a particular wheel load, and the payment load and the vehicle load has to match. Or if the load on the from the vehicles increase beyond the design load of the payment will fade fast. So we'll have to ensure that the vehicles which ply on that particular road is actually below the particular approved standard weights. And that can be ensured by weigh in motion systems. So if there is more weight, probably you can charge more toll to that particular vehicle, or you can probably discourage those vehicles to go in a particular lane which is not designed for a particular weight. Okay. Similarly, crash analysis, EAA, okay, and also the alternative highway regulatory and investment policies. All these are based on the vehicle counts and classification. Now there are Detect technologies. This is actually which has been discussed many times. That is, there are in situ, intrusive, and non-intrusive technologies to classify vehicles. Intrusive systems are the one which is either mounted below or at the surface, whereas non-intrusive technologies are what you call it, camera-based or sensor-based, which does not have to have a physical contact with the vehicle, which are mounted at an elevated gantry or by the side of the road, or such systems where there is no disruption and it's not conspicuous to the road users, which will be outside the road. Okay. Now this is one of the intrusive technologies detailed here. The system which is numbered as 1 are embedded magnetometers. The number 2 is pneumatic tube detectors, okay, and 3 inductive detector loops. So I think the inductive detector loops are increasingly used by law enforcing agencies these days in India as well. That means we have a series of inductive loops, and when the vehicle crosses over the loops which are buried below, just below the surface, the change in the magnetic flux that is recorded and taken, and when there's a violation of speed between these two inductive loops, that will trigger a camera to capture the image as well as the video image. Okay, that is how the inductive loops work in tandem with the video-based surveillance system. Then, as I told you, the weigh in motion is either to have a strain gauge based or the piezoelectric based. So there is a plate which is kept at the surface level, and when the wheel rolls on the plate, either the strain gauge which is kept below the plate is activated, or the piezoelectric system which will be fired, and you can measure the weight. So that's a measurement of how much axle weight or weight load is applied onto the plate. Now this is the typical system which you can see on the road. Here you can see how the weigh in motion plates are kept. It is at the same level, and that is also supplemented by inductive loops. So when a wheel load comes, you can see the plate get deflected. The span is sufficient so that the weight is taken by the plate, and here you have a sensor, and that is measured or as the dynamic load. And once you have the dynamic load information, the static load can be taken from the calibrated dynamic load information of that particular product. So what we need is probably the static load of the vehicle. From the dynamic information, probably you can convert that to static load scenario. So this in 2017 paper, Barnos and Rice have documented what are the different technology available in weight motion, right from a polymer sensor, the quartz crystal, then a fulcrum which moves as the plate, and also an aluminum extrusion insulator and copper electrodes which press each other so that the weight motion can also be found out. Now this is from the Federal Highway Authority, that is FHWA. We can see that the inductive loops and the strips which are kept for W in motion. So often what we do is a single system of weigh in motion is not sufficient. Probably we may have one more set of weigh in motion strips, so that even if there is a mistake in one of these, can be captured by the next one. This actually work in tandem. Similarly, the inductive loops, it seldom provide only one loop. So there is always a redundancy that is given by another set of loops, and that is taken by a sensor and what you call it, a computer, and that can be processed. Now, going to non-intrusive technology, often what is done is you have probably a gantry over which. Hello. Okay. Is there a disturbance in my voice or what? Okay. Hello. Is it okay?
Yes, sir. It's okay.
Okay.
Appu sir, please mute the participants. Okay.
Yeah, fine. I thought my audio system. Okay, doesn't matter. We'll continue. So non-intrusive technology, we can see that there are three possibilities. One is provided on a gantry, or second is roadside mast, or you can even have a crossfire. That means you lay or keep this across the two sides of the road, and when the beam is cut, that is an incident. So that can be called as a count or type of vehicle or whatever. We'll come back to that later. And then the video image detection. So as I told you, video image detection, it sounds very simple when you say that, but when it comes to reality, there is a lot of problems. Like, we'll have to analyze this by frame. So that means, if you have a 30 frame per second video coverage, and for 1 minute, roughly you may have, depending on the quality of the images, you may have something like 50 or 80 MBs of data to something like 250 MBs of data. So imagine that we have 1 hour data and collect that in a system and try to replay that and find vehicle incidents and type of vehicles frame by frame. It's going to be a phenomenal task. So the computing time is going to be very high. So we'll have to be very careful as to how the incident is detected and the vehicle is identified. So there are emerging methodologies by which we are trying to perfect the quality of our data, the quality of our analysis and interpretations either by going for some neural network technology or modified technology like CNN and whatever. Okay, I'll come to that later. Or just look at this. There's a highway system in the West in USA where you can see that there are 10 or 12 lanes on which there is same type of vehicles present. So this is not going to be very difficult as far as machine identification is concerned, because the frames are sort of defined, the vehicles are sort of defined. So if you can identify a vehicle, that may be an incident, that can be a count. But in one of our studies, what we have done is that instead of having the vehicle video image processed, we have recorded the sound by sitting by the side of the road. And we can see that sound recording as given in the first one here, this one, okay, A. And that is transformed to its short-time energy. So we try to find out the energy peaks of that particular sound recording. And we can see when when the peaks are identified, the incidents are the vehicle incidents. So we don't know what sort of vehicle are coming, but every peak, every spike in the energy level is indicative of presence of vehicle. So probably that may be good as to say how many vehicles are flying. If you have a homogeneous vehicle system or scenario, probably the sound itself is going to be helpful, because the file size of the sound recording is much more simpler than dealing with your image file, okay, or data requirement is less. Now, in India, one of the company which has developed this technology is TRAZER, which I'll just tell you what are the possibilities of this particular system based on the TRAZER experience. TRAZER is actually traffic analyzer and enumerator software, where you have urban and city traffic study. You can have the capability of billboard analytics and speed lane detection and speed and lane detection and video-based incident detection. Then congestion detection, okay, dynamic traffic rerouting and city surveillance. All these are possible by the TRAZER, or can be upgraded its capabilities to suit your requirement. Now, what do you mean by urban and city-urban traffic study or city or urban traffic study? Now, one could be the gap analysis. So what do you mean by gap analysis? Gap analysis, how the vehicle successively arrive at a particular position. So whether this gap could be an indication of how well the vehicles are packed in the system, or if you have an assisted or vehicle what you call control system, for example, assisted drive technology, the gap could be further reduced. That means you may probably have more and more vehicles. So typically, how much gap an individual driver leaves between two vehicles, whether driver is actually can be modeled based on his following the predecessor or the one which is on the front. So how you can capture that? Then second one is lane occupancy. The lane itself, there are vehicles which occupy the center of the lane. There are tendency to move to one side or left side. So there is a lot of variability as far as the lane occupancy is concerned. So that also can be effectively studied. Especially that has got some relevance when you try to understand what is the psychological spacing which you required when a two-wheeler is traveling by the side of a heavy truck, or how well how different he is going to behave when he is actually traveling by the side of another two-wheeler. So this is actually can be studied if you have a TRAZER system. Then behavior of one of the class of vehicles in presence of other, that's what I told you. Then headway analysis. Then general wear and tear estimation of the road, etc. can also be modeled. Then probably something which has not been thought is that the billboard analytics. So we have done a study to find out what is the influence of the roadside hoardings on driver attention. So the other way around, if you put up a board deliberately and to see how many road users are actually looking onto that and how long they actually view that particular billboard or any traffic signage. So there you can probably have a camera, and then later you can probably analyze and to find out how long your eye is fixed onto the particular information which you are trying to convey. So that's again a possibility which is used both by law enforcing agencies as well as advertisers. Then is the lane and speed detection, or speed and lane detection. Okay. Now we can find out the trajectory of the vehicles, and the trajectory can be analyzed to find whether there is an impending collision or an accident with another one. So that is called time to collision or collision. Okay. So so as a basis of that, we can use this to find the trajectory information. That means how the vehicle is actually moving on the road, especially when you negotiate intersection. Okay. Now next one is video-based incident detection. So suppose you have a route in which the traffic goes below a certain threshold or a particular speed. That's an indication of something wrong. Whether there is a lot of vehicles in the system, or whether there is an inefficient signal on en route, or there's an incident. Okay, and that can be understood if you have a analysis. That is also possible by a proper what we call it video analysis software. Then congestion detection. So congestion could be different at the time or different times of the day, different at different times of the year. The festive seasons, it could be different. Different weather conditions, delay could be different. And weekdays and weekends, there could be a difference. Okay. All this are congestion, and study will definitely throw light as to what is the micro level intervention which you require so that the congestion can be mitigated. Okay. Now, this is again infrared sensors, which is extension of what we were discussing earlier. That is, you can see that there is an incident ray and a reflective ray, and analyze these two rays and find out at what speed this is moving. And road surface and the vehicle will have different reflective possibilities of emissibility or emissivity. So that is taken as what we call it an incident or a vehicle arrival, and the speed can also be detected. Now again, non-intrusive techniques other than the video sensors like TRAZER, I told you, the infrared sensors. So the active infrared sensors or AAR lasers, or there are LEDs or lasers which are kept on a gantry, which gives a continuous beam down to the road surface. So when a vehicle crosses this particular beam, that is taken as an incident. So there again, the reflection or the return wave or returned what you call a beam is taken, and that is found to be what you call it an indication of vehicle is moving, and can be understood as a speed estimate or the what you call it the type estimate. Okay. So here you are using the Doppler technology, and you can see the laser radar beam geometry which is kept on a gantry. And if you don't have permanent fixtures to do this, there is short-term data analysis required. There is one beautiful instrument these days. I think some of you might have seen this. That is the TIRTL, the infrared traffic logger. That is TIRTL. It has got two units which are used to find the speed, to find the type, which is actually based on a light-based technology, non-intrusive. So two units will be kept on both sides of the road, and their speed can be found out. The lane and lateral distance between vehicles can be obtained. The classification also can be obtained when you have multi-axle vehicles crossing. That spacing and timing can be reflected as the multi-axle vehicles. So here there are two receivers. One is the receiver and the transmitter, two devices mounted on each side of the road. Two infrared light beams are emitted. These light beams are separated by 153 mm, and as the vehicle moves, they cut these beams. So when the beam is cut and then restored, the TIRTL receiver detects that as an event, and depending on how long this is cut and restored, that is evaluated as the speed of the vehicle. And how many times it is cut, that also is indication of the axles of the vehicle. That is actually a reflection of the type of the vehicle. So the TIRTL beams can be used to find the speed of the vehicle, as well as how many times has been subsequently cut. That is a reflection of the axles. So here you are actually concentrating on one lane. Suppose you have multi-lane road and simultaneous arrival, there could be some errors in the estimate in the TIRTL is concerned. So that is one problem with the TIRTL, but TIRTL is a very effective thing. So here what we see is actually how the speed is estimated. You can see that there are two rays which are emitted by the transmitter and two rays go into the receiver. So these two are not in the straight line. One is having a straight line incidence and the other one is inclined. So depending on where it cuts, you can see that the time of interruption will be different. So we can find out where exactly the vehicle is positioned and how fast they cut while it is moving in the forward direction. So that is measured as the speed. So on the right side, what I've shown you is the TIRTL instrument which is kept on the road. This is actually a very mobile thing. Two units are required. We can be mounted by the side of the road. We can collect data and then go. So this is for a short time classification count, short time speed estimate, and axle count or whatever. Okay. Then another very promising area is that of the enforcement, that is red light violation. So I think all of us have seen in some in our states that we have red light violation detection in intersections to find whether the vehicles jump red lights. So when they jump red lights, the snapshot is taken, the number plate is captured as well as a very short video to substantiate that particular vehicle is violated. Okay, so this will be sent only when there is a violation, that will be sent to the server and that further challan will be issued. And automatic number plate recognition system also is now it's coming. So the problem with that is actually the background, the weather, the type of lettering, the cleanliness of the plate, all this will affect the number plate recognition. Okay, so this is the typical arrangement which we have in our state. That is, you have sensor loops embedded on the road, and once you violate a particular speed or violate a red light, and that is taken by a still camera on a mounted gantry or a post, and also a 3-second video camera to substantiate your claim. Okay, so there are RLVD or red light violation detector controller. Then that information alone goes to the server and ticketing is done. So many times automatic ticketing is done, but sometimes the manual intervention is carried out. In the server, people will sit and manually dispatch the challans. Okay, both are possible. Now, which is explained already, that is, we have two loops. The first loop is on video recording. Second loop is for snapshot by still camera. And if the first loop is touched, the video is discarded and the signal turns green, and the video and snapshot presented for processing. So we take the video and video is on, but only when there is a violation, then the video is recorded and kept. Otherwise, it's not. So that is how the RLVDs work. Okay. Otherwise, data will be so enormous, we will not be able to process that at all. Now, this is one red light violation example in our state of Kerala, that we can see that we can see the number plates, which is clearly shown, and also there is a video footage, and the number plates identified to that of particular user, and the penalty amount also is given, and you can see the status of the payment. So if you log on to your RTO site and give your vehicle number, you can find out if there is any existing challan, and from there you can pay the penalty. Okay. Now the issues or challenges are nighttime identification is difficult. Inclement weather conditions, it is very difficult to identify, and different types of font. Even though we have standardized the fonts and letters, people often use different fonts. That is a problem to identify the number plates. Then untidy number plates, poor lighting, heterogeneous traffic, multiple violations, poor latency, all these are challenges. So our system, when you perfect, so we'll have to have all random what you call it process here in place, so that all this can be captured, so that your robust system can be made. Now here you can see one of the method to identify vehicle is probably to use the RFID tags. Now RFID tags, as you know, that the past 10 years or so, in all vehicles which are manufactured in India has a RFID tag fixed onto the windshield. So it has got information about what is the chassis number, what is this engine number, and probably we can have the information of the the owner's detail also into that RFID tag. So when a vehicle crosses this gantry where the RFID detectors are provided, we can really identify which vehicle is that. That also can be used even in the case of tracking a stolen vehicle. Okay, so this is not been done so far in a large way, but experimental purposes we have been doing this RFID tag based vehicle locating and identification, so that even travel time across a particular stretch can be identified if that particular vehicle with a specific RFID tag is detected at a later point of time. Now you can see that this is a process. You have the RFID tag stuck onto the windshield, and there's a gantry which shows the RFID readers are there. So from a distance, the vehicle can be identified, and that can be decoded and presented to the system. So the speed violation also challan can be identified or given just by observing the RFID tags. Then we move to a vehicle actuated traffic signal, which is a very promising area as far as the advancement is concerned. You have a demand actuated and area traffic control system. Okay, so we've been doing fixed type and manual control system, and traffic controllers are either manual or fixed. And now we have moved to demand actuated and area control systems. Now in the fixed time controller, the problem is that you have a specific duration of green times, and the timings are fixed. Now, if there is a lead demand, and if still the green is shown, so that will be a concern, cause of concern, because driver frustration and lack of confidence of that system will be more if there is green provided and there are no vehicles at all. So why this happens is we are using the historical data. The historical data, the data collection accuracy will depend or largely result in the design of the signal. And also that now we'll be using something like not the peak demand, we'll be using somewhere in between, like something like, we call it as 30th highest hourly volume and demand. That means there are some point of time, some hours of the time where you have larger demand, and signals will fail. Okay, so there is going to be congestion. Now, these are all techniques by which you can probably have vehicle actuated signals, because you have inductive loops, which I already told, which can be picking up the arrival of a vehicle, pneumatic road tubes, micro loop ports, and things like that. Now, if we have all these systems connected, and we can see that if only there is a demand, the controller will apportion a specific time for the for the signal. So if there is no oncoming vehicle, we do not have to have green given at all. So probably one green can be cut. So this is what is known as vehicle actuated signal. Or you have a very small time segment given in a green, and increment is given only when there is specific vehicle coming. So that means there is some minimum green is given. That is maybe sufficient for a few vehicles only. And if there is continuous demand from that particular leg, you extend it further so that more time can be given to the maximum possible. Okay, or as envisaged by the maximum possible timing. So that could be one method of vehicle actuation. Or the other way around, if there are no vehicles, you do not have to provide green at all. Now the wireless system WiTrac is actually to have a standalone independent system where solar panel and power is given, and vehicle is detected, and timing is controlled by the WiTrac equipment. So typically every island has a slave controller and has a solar panel, and the controller and the units is kept by the side. So we have sensors which are connected to the controller at the particular specific location, which are isolated, which is not controlled by a single controller. At the intersection itself, we may have the what you call the master and slave controllers. The slave will talk to the master controller, and the timings can be apportioned depending on the vehicles. Now, another challenge is that now we are talking about ITS. intelligent transport systems. So one of the important aspects of travel time estimation is to find how what you call it realistically we can find out the travel time. So there are different things. One is to introduce test vehicles. Second is to identify license plates matching technology. Third is ITS pro vehicles and non-traditional techniques, which I also will discuss later. Now, in-vehicle technologies of floating car data is essentially to use GPS-based floating car data. That means when the car is moving, the GPS system on board the car can be used to find how it moves in the traffic. So when this is picked up by another what you call it server that is transmitted to another location and can be processed, that's an indication of what is the current estimated travel time in a particular network. So data of car location and speed and direction of travel are sent anonymously to a central processing unit. So you don't have information of which car is moving, but you have a feel about this probing car or probe car or the floating car is actually moving at a specified speed. So that is an indication of how fast the traffic is moving in that particular leg or a particular road. Now, after collecting this, you pass this on to prospective users. So that if there is a congestion in one of the leg, or if this is going to be the estimated travel time in a particular route, the users will have this freedom to select an alternative route. So this is an in-vehicle floating car technology using GPS data. Okay. Now, as I've already told you, radio frequency identification tags or RFID tags. So the RFID tag of the vehicle, if it can be what you call it, can be read at a particular location, and subsequently at a second location, if the same RFID tag is read, the time taken from the first reading and the second reading will be indication of how fast the vehicle is moving. That's the indication of travel time. That is the real travel time measurement as far as that particular day at that particular time, how much time is going to take. So that is passed on to the people through central server, and we can probably have a very realistic estimate of how much travel time is going to take in that particular route. Okay, this is what I told you. This work carried out in Kerala in College in Trivandrum. You have an RFID sensor and also a Bluetooth sensor. Both are used simultaneously, and to see both if they are okay. And there is already a published work and which is by Jain and Anusha in 2020 to find the travel time prediction under mixed traffic conditions using RFID and Bluetooth sensors. And they found that RFID tag or RFID sensors, RFID tags are useful to find the real travel time between two locations in a city. Okay. Now, in ITS, we can think of vehicle probes or probe vehicle data collection system. So there is one signpost-based automatic vehicle locator or AVL. So here what you can see is that on the post you have a sensor and location antenna is kept on a vehicle, and that information is passed on to central computer, and that is passed back to the users. So in fact, one of the vehicle is used as a probe vehicle. Probe vehicle is actually a test vehicle or a vehicle which is designated to move around in the traffic, which has got a particular system in place, which is a location antenna and receiver, transmit receiver, things like that. And on the signpost, we have a receiver and transmitter transmits it to a central computer, and that is processed as the real traffic or what we call it, the travel time at that point of time. Okay. And second one is automatic vehicle identification by probe vehicles. Again, the probe vehicles will be having electronic tags. These electronic tags are equipped to communicate with transceivers by the side of the road. And these vehicles may be very unique vehicles which are equipped. Okay, this will be continuously moving in the traffic. So we don't use commercially available GPS. We may probably have a test vehicle in the traffic so that the travel time requirement or data can be found out. Okay. And Third is that the ground-based radio navigation. So here, when say for example, before the Uber and Ola used to come based on your internet-based booking and dispatch system, there were a time when each and every taxi operator used to have a dedicated radio frequency to call them and address them. Okay, so when you make a phone call, the phone will picked up by a central operator, and he will note your location, and the location will be passed on to the nearby vehicle through a radio message. Okay, so they tune to radio frequency, and the radio message of that particular taxi will be to direct you to a particular address. So that is what the ground-based radio navigation was all about. So now GPS is used. Now the internet facility of dedicated softwares are there to dispatch vehicles to exact positions. And if you use or subscribe to this particular utility, we know that how or where your pickup vehicle is coming and at what speed is coming. Similarly, the same can be used if you have prop vehicles, and through the traffic, if it can be monitored, we can that can be an indication of how fast the vehicle is moving in the traffic. Now, this is one of the emerging areas I told you, that is to use a cellular geolocation. Now, it's an experimental technology. Now, a lot of data is being collected by Google and such service providers. Now, whenever you connect your phone to Google network, so actually you are actually giving certain information as to where you are and at that point of time. And if you are on a move, the progressive location which is connected by your GPS position give you an idea about how much travel time is required. Now, this is actually collected and processed and given to other users as well. Okay. Now, cellular phones also can be used to collect travel time data. So, from one cell to another, how they move, even without your network data or network coverage. Okay. So, these two techniques have been applied, which is used in cellular technology, cellular telephone reporting, and cellular geolocating. So, geolocating using the Google platform applications has been used by traffic engineers to find out how your network behaves in a particular day or a particular time. Okay. Now, these are the other traffic engineering issues. Like we are trying in the process of developing systems for following distance warning. So, suppose a vehicle follows another vehicle. There should be a warning as to you're coming too close to another vehicle. Then systems are being developed for adaptive cruise control. That means it's not a fully automated cruise control. You are actually something like a semi, what do you call it, cruise control. You have an adaptive cruise control. Then lane departure warning. So even 10 years before itself, you know, there were cars which were equipped with lane departure warning. That means the car will be sensing the lane markings, and when you deviate from that lane marking, there is a warning. Or there were cars which were developed to track the lane markings, and they were to be what you call it on an assisted mode. It's not a fully what you call it driverless option. You have an option where you can take over the control if the car misbehaves. So basically your car will be following the lane. Okay. Then assisted parking system. So this is very common to these days new gen cars, that you do not have to sit in a car to park it, especially in tight spots and difficult places. The system, the sensors, and the car itself will go and park it. Okay. Then intelligent speed adaptation, especially when you're moving in a platoon. The speed has to be adjusted real time. That means the sensors should talk to the vehicles in the front and adjust the speed. Similarly, the vehicles in the back will be looking at what you are doing in front, and then the speed can be adjusted. Okay. Then seatbelt reminder and unlock, electronic driver license, collision avoidance, and braking systems. Okay. So one problem which in India see is that now when we have advanced system of collision avoidance and braking system, each and every incidents or intrusion into the to the frontal area of the car is will result in a brake application. So if you cannot ensure a certain discipline in our operations, then this assisted system will have a lot of problems, because the system will interpret that as an impending what you call collision. Okay. Uh, we are now in the process of developing systems which are suitable for India. Okay, so how the driver variability and the system characters can be embedded into your design philosophy, especially for cars which are brought to India from other manufacturers, for example, European cars and advanced car, to be Indianized so that this can work well. So this is a very challenging proposition as far as concerned. Then blind spot detection. So the rear view mirror has a blind spot. So if systems can be developed to find the blind spot, avoid blind spot, certain accidents can be avoided. For example, when you want to turn to the right, and if there is a two-wheeler by your side, and if he happens to be in the blind spot, you will not see that vehicle. So then there is a chance of you meeting with an accident or hitting that particular two-wheeler. So blind spot detection and warning should be in place. Okay. Then vision enhancement system. Okay. And pedestrian detection system, reverse collision warning, alcohol interlock, fatigue warning system. All these are being developed and given to vehicle production. Okay. Especially fatigue warning. So there is one system which I have read in some time back in one of the journals, is that it was there some years back. The impending sleep is monitored by the movement of the eyelids. So the eyelids will blink at a certain rate. So when you are about to sleep, the blinking rate will be different. So the system will process the time of blinking of eye, and when you are sleepy or when you want to sleep or the indication of sleep, there is a larger time duration for you to blink, or time take to blink will be more. So that is taken as a warning, and systems can either be on a lock mode, or the driver can be alerted that you are going to sleep, so that he can take rest by stopping the vehicle. So there's a very simple system. It's a fatigue warning system. Okay. Then we will be seeing a lot of dedicated short-range communications in future. Like already we have a lot of systems in place. Every manufactured vehicle has an onboard equipment. So onboard equipment is a computer which can convert, talk to roadside equipment as well. So the performance of the vehicle itself can be tapped from the onboard computer, or this can be made to communicate with roadside equipment, and that information will go to internet and to the cloud and the servers, and this can be processed and can be relayed back to the other road users. So similarly, emergency vehicle signal and signal preemption. Now this is one of the challenging areas, because ambulances, fire tenders. So when you are in a city, when it's a congested city, if an emergency vehicle happen to be on the road, how will you manage the signals? The signal timing should be altered to accommodate the oncoming emergency vehicle. See, the issue is that when this siren is heard, either the siren sound can be picked up by a sensor, and that audio signal can be used to process or give exemption or give extension to the green time. Or you can have a dedicated emitter or signal emitter that can be picked up. So in one of the studies which we have carried out, what we have done is the siren of the ambulance or the emergency vehicle was picked up by a recorder. Okay. And this is processed and identified as an oncoming emergency vehicle. And the timing of the signal is altered. So if it was red, immediately the green was given to that particular phase, or if it is already green, extension of time for the crossing of the emergency vehicle is permitted. So that is a possibility in vehicular operations or emergency vehicle operations in a city. Now, this again is the same schematic of the emergency vehicle operation or preemption. So you can see that the onboard vehicle, onboard equipment is emitting sound that is, or RFID tag is there, that is picked up by the roadside sensors, subsequent sensor also. So that two sensors will indicate how fast the vehicle is arriving at the intersection, and that is passed on to the roadside communication equipment. That is again going to the controller, that is the signal controller, and that signal controller will alter the timing of the green at the intersection. So till such time the emergency vehicle is there in the particular approach as well as intersection, no cross traffic is permitted by the control, because the control overriding is now done. The timing is now overridden by the emergency vehicle. Okay, that's a very good system, which is an advancement we have seen in the traffic engineering and management. Okay, now we move on to some of the work which we have been carrying out, which is very promising, which I just want to introduce because it's not been widely come in textbooks as asset. So we use signal processing approaches to speed estimation, vehicle detection, and vehicle classification. I'll show some of the work which have been carried out, we'll be doing. This is one work which we tried to find the speed estimation by video-based data collection. That means, is it possible to have two cameras separate at a distance and collect videos, and then this video information could be used to find the speed. So what is speed? Speed is the time taken from the vehicle to move from one location to another location. So typically what we use is a time measurement from location 1 to second location, either by some advanced method or simple method by which a stopwatch is used to find the time. So instead of that, what we use is we are using two cameras. So the video footage of these two cameras is taken to a computer, and these two streams are now compared, and similar vehicles are matched. Okay, so from the start, after a phase lag, if a vehicle is seen on camera 1 or video 1, and that is an incident, and the same vehicle when it comes to camera 2, the time separation is measured, that's an indication of speed, which has been very good. And this is a system which we have used, that is camera 1 and camera 2, which is used for data collection. And some algorithm is used to find the region of interest detecting use mesh network. It is actually the what do you call it, video processing techniques, which I am not going to discuss here. And after which the extracted image, something like, we have a technology which is called a SIFT, that is scale invariant feature transformation or transforms. SIFT that is used, and both SIFTs are matched, and if they both are matching, that means it's a single vehicle, and that time lag between the first image and the second image used got in the second camera is a speed estimate. Okay, so that is how we found it. So this is actual work done. We have done the work. We can see that there's a Omni van which is presented in a series of vehicle, and the vehicle is identified by an image here, the first and the second one. So that is actually an incident which is now at a time separation. So that time is measured to find the speed. So a two-wheeler, a three-wheeler, a car, a truck, again a two-wheeler. So all these vehicles were identified in two different locations, and the time separation is measured and found the speed. Now look at the part of the success of the particular estimate. We did some calculations, and we found that the radar speed gun estimate and the estimated speed with our methodology, the mean square deviation is around 8.4, 2.23 in one of the data sets. So it's very small, 2.23 kilometer per hour is the deviation in one of the data sets. Okay. Then another one is that we checked whether we can use sound signature for detection and classification. So whether the sound generated by the vehicle is good enough. So as I told you, if you go to video-based recognition system, the image size will be very high, and the processing time also will be very high. Whereas if you use only audio signals, only sound signals, the file size will be very small. So we can see there are four or five different what do you call it, plots, in which one is the simple waveform. That means a sound in the crude form is captured, and then we can find out what is short time energy from that, and then the last one, that is a peak. That is, whenever there is an incident, the energy will have a peak. So these peaks will be corresponding to vehicle. So if there is a specific sound emanated from a particular type of vehicle, and if that is that can be identified at a particular energy level, then always that energy level will be corresponding to that particular type of vehicle. For example, if you have a car and the car has a particular predetermined energy, so which you actually use for your training purpose, and once the network is trained using a multi-layer feed-forward network, with the structure which you have told us 30L, 35, and 10 and 4N, that is linear and non-linear, what you call it, layers and neurons, and it has given an accuracy of 67%. So if you are interested in only identification for a what you call it, understanding purpose, not for enforcement or something like that, 67 is a very good percentage for an audio-based vehicle detection and classification. Now, if you add audio to video, so the moment the video is added, the accuracy percentage has gone to 82%. So in this, what we do is the audio signal is taken, and the audio signal analyzed to understand the peak where the vehicles are present. Now, on and in and around the peak, only those frames of images are taken. The first task is to take the audio or the video footage in which the audio is now intercepted, and wherever you have the peak audio information, and from both sides you take only the frames of videos. So that means the size of the data or the file is going to be significantly less. So we are identifying only the peaks, and images on either side of the peak is taken, and that is used to train our network and also for the classification purpose. So with that, again with the multi-layer feed-forward neural network, we have seen that the accuracy has gone up to 82% in published work in 2016. Now, where the camera was kept at 5 meters from the road on a tripod, and the system was actually to use audio signal, and once the audio level is passed, then only the video signal is used and for the classification and identification. Very promising as far as we are concerned. Okay. Then again, we used the same technique, with the multiple feature-based classification process, like audio and video. What I am trying to tell you is that even when you have state-of-the-art off-the-shelf products, now the accuracy level may be very low. Even in the case of TRAZER, the accuracy level is slightly less. Only practicing engineers would know that. So the effort is to enhance the accuracy. So our understanding is that if you again separate audio and video and then use some CNN-based classification, probably you have better or a robust classification system. So for example, you extract audio and detect the peak of the audio. That means that's the incident where the vehicle is coming, and then you try to match the frame, and if the frames are not matched, discard it. Only the frames which are matched, you take it to the matching, and then you extract the features, like what are the different, like on different system like AUG, HBB, and case, and things like that, or CNN, and then you can classify two-wheelers, three-wheelers, car, and any number of trained network can be obtained. Now, in this particular study, we have used two cameras side by side. One is a mounted camera at a height, and also a roadside camera. These two frames identify to identify the peak short time energy with audio, and then one is used for audio detection, other one is used for video. So one audio feed is given from one of the source, and when the audio is detected, you take over from the video source. That is how the training is done. So this is the schematic. You can see the side camera will feed in the audio, the top camera will feed in the video. First you process the audio and extract, and then you detect the peak, and only at the peak you go to the video source and pick the video image from the other system. And then the matching is done, and the vehicle labeling is done, and classification is carried out. Okay. Now, the confusion metrics or the success has been documented here. You have, let us say, a two-wheeler, three-wheeler car, HMV, the heavy vehicle, motor vehicle, and light commercial vehicles. We can see the two-wheeler, known two-wheeler and predicted two-wheeler is 6. Two-wheeler to prediction of three-wheeler has been high. So in the event of two-wheeler, there is a lot of confusion as far as two-wheeler to car. Whereas to car, it's a very high correlation. That means a car which identified a car and predicted car is very high. This is actually a first trial only. We are trying to perfect that. And similarly, HMV. So HMV, known HMV and predicted HMV is very high. LCV also very low number in this particular data set. It is 2 and 3, but it is promising. So only thing is there is a confusion of three-wheeler and car. Why? Because the three-wheelers these days is as big as a car. Okay, so that's why even the sound, when you take the sound and video and vision and all that, there is still chance of errors because of the size and such matching technology. Okay, so that is where we like to address. So car and two-wheelers, there is a lot of mismatch. Car and car, there is not much. So this is the confusion matrix. Okay, so I think we are trying to the close of the discussion. I think I am not overshot the time. Really 1.5 hours, you said. So let me conclude. So there are many new technologies available. Now we are now dealing with lot of emerging technology from various fields of engineering. So that is integrated so that your traffic is behaving well and efficient, and your everyday commute is a more pleasurable experience. Okay. Now you cannot differentiate electronics or signal processing or computer or artificial intelligence or machine learning or soft computing needs to their own field. So we are trying to bring in all those advancement into traffic engineering as well. Now, our thrust is on accurate data collection. So data collection has to be perfect because a lot of challenges are there in our case, especially because of heterogeneity, especially due to change in climatic weather, due to different types of vehicles and different types of number plates and operating characteristics. Also, there is a lot of challenge involved in accurate data collection. So data collection, once done, the processing and remedy measures is a very big challenge, because I've told you, voluminous data itself is a problem. Like, you don't know what to do with that. So it's all useless, if you don't know what to do with that. Okay. So there is always a thrust as to how data mining can be done easily, so that we can probably learn many trends so that the remedy measures can be taken. So again, artificial intelligence has come a long way. We are able to find out incidents or predict incidents. Okay, how and when this is going to happen. So remedy measures can be taken. Okay. Then novel and efficient systems of traffic management will hold key to the overall growth of any country. So as I've told you, we are trying to perfect cost-effective and efficient system by going into unconventional domains, like how speech, the audio and video can mix so that we can have a better system in place, rather than only vision-based systems where it is computer-intensive, cost-intensive solutions. Okay, whereas if you can develop simple systems, which probably will be worthwhile for a country like ours. So I think, within this specified time, I think I have given you a peek view of what is traffic engineering and where we are going, and what you can expect in near future, how your system can be improved, and what are the areas where you must be reading if you want to know more about the developments. There are IEEE transactions in Indian transport systems which bring out the developments in this particular area, especially on what you call it, data collection and algorithms and things like that. So please read on to those transactions as well, so that you can have a better insight. I hope I have covered, justified, and if you have any specific queries, that will be addressed now. If I can address those, I'll do it. If there are some questions which I am not able to address, you can take down my email. My email address, I'll just type it out on the slide. Okay, note down. Binoy Koshi at amaljothi.ac.in. I hope you can see this. Okay, that is my email address. You can address me. Okay.
Thank you, sir. Thank you for the very informative session. Dear participants, if you have any doubts, please interact with our expert. Participants, the session is open for discussions. In case of any queries, please do interact with our expert. Chat box.
Yeah,
there is a question in the chat.
You can put in the chat box. The question is, sir, would the sensors and cameras be efficient in case of snow, foggy, and rainy conditions? This is exactly what I told you. There are challenges. There is a challenge. Okay, that's why we may probably have to have multi sensor systems in such locations. If it's a critical location where you don't want to what you call lose any information, probably we may have to have multiple sensors. Okay, so that even if one of the sensors is not able to pick up the information, the other one will be able to do it. Okay, and the challenge is this, like inclement weather conditions and snow and foggy conditions and rainy conditions. Difficult, of course, but see, even when you, for example, if you record the audio, the background noise can be detected. Suppose a car goes in a rain, the sound of the rain can be detected in that. So that is the sound of the car itself can be a clean data. Okay, such techniques are available. Even when you have a very noisy data, it can be cleaned, possible. But that is a research challenge, of course. Yes.
Participants, any more questions? Somebody's typing something in the chat box.
Okay.
കേസിൽ ശരിക്കും പോവാ എങ്ങനെയാണോ പോയിട്ട് പറയാ നിങ്ങൾ ബാബു കൂടി കൊടുത്തൂടെ ഞങ്ങൾ ബാബുവിന്റെ പേരിൽ വിളി കൊടുക്കില്ലേ എന്ന് പറഞ്ഞു. അപ്പൊ ഒരാളെ നമ്മൾ പറഞ്ഞാണ്
Some disturbance is coming. Participants, please mute yourselves.
Okay, the question is in the case of self-driving cars, how the speed is monitored. I guess the protocols are being developed. Okay, assisted mode or driverless mode. Driverless mode is basically with sensors. Okay, so the speed has to be adjusted with the stream speed, so not the speed which you select. So suppose you are moving in a stream, the speed has to be adjusted with the speed of the other vehicles around you. So that way, speed is not to be monitored in the sense for that particular vehicle. Suppose you want forensic information, the speed profile of that vehicle can be captured later. So I think that is what you mean. Or you can probably use that as a probe vehicle and find out how it is actually behaving in a predominantly driver assisted driving versus self-driving car. Okay, that if that is the case, we can probably have an insight. But at some point of time, most of the cars may be self-driving cars, or then you can have more and more cars at close intervals. So because because it's all machine control, you need not have to have so much spacing between two cars. Okay, so that way the future would be we will be having more capacity to the system because all cars may be driverless cars. Vidya, why this what is shown is temporarily joined and unable to chat or something? Are they trying to stop?
Sir, actually, no, sir. Actually, in Teams, we can see such messages. Usually, we see that in the chat box. It comes in between.
Okay, I thought because they are not in the same domain, probably that's not been allowed. Is it?
No, sir. Sometimes maybe some of them have left. That is.
Okay.
Okay.
Vinod sir.
Yes.
Sir, I had a query regarding you explained about on a study like emergency vehicle signal preemption.
Yes.
So about that, the sensor that has been used there does it have any special properties or something compared to the other sensors which we use?
In the case study which I mentioned, that is actually a sound recorder. Okay, that picked up the siren sound of the ambulance, and that was processed as. See, that's a very unique sound, right? That frequency is unique. That sound is unique. That has been processed and given as a instruction for extension of the signal. That was a study which was carried out and presented in one of the international conference of IEEE, and the student was funded to go and present this work. I don't know the other systems which are being manufactured by the companies. Like there could be systems where this frequency can be picked up and can process. I'm not sure about that, but we have demonstrated this is possible by just picking up the siren sound, the sound of the siren of the ambulance or okay. I hope that's clear. It's actually an audio capturing device that is processed by the computer, and the computer will detect that as an incident, and the time of the the green time will be extended, and in that particular approach alone.
Okay, sir. Thank you. Sir.
Hope I have explained that. Okay.
Sure, sir. Sure. So if there is there any difference like for the ambulance or the fire engines or something, the siren? Is there any difference among those emergency vehicles, or it's same for all the emergency vehicles?
Now, see, the issue is now we should be able to understand at what speed it's coming, whether it's actually crawling in the traffic or is it coming at a very high speed. So the change, the change in the intensity of the sound, okay, and how far it is detected and how fast it is being picked up. That itself is can be processed by the machine. The unique sounds can be detected. Like for example, the ambulance siren or the bell sound of the fire engine. That's a very unique sound, which is not similar to a horn. Or actually, what you do is actually you are training a network. Okay, So your network is trained to understand only the designated sound. So when that designated sound, the next question is to understand how far it is. Okay. So some calculation as to how far it is coming and whether you are already in the green. And if that is already in the green, now try to extend the green time. If there is no green at the particular approach, you try to give the green at the highest, next opportunity. That is how this is done.
Okay, sir. Thank you, sir. It was a really informative session, sir. Thank you.
Okay. Okay.
Matthew sir, can we move on to the vote of thanks?
Please move, Vindhya Miss.
Okay, sir. Now I welcome Christy Francis Lone for the vote of thanks.
Thank you, Miss. Okay, good afternoon, everyone. It's my privilege to have been asked to propose vote of thanks on this session. I, Christy Francis Lont, on behalf of the Civil Engineer Department, College of Engineering, Kidangoor, extend a very hearty vote of thanks to our expert, Professor Binoy Koshi, sir. Thank you, sir, for accepting our invitation and for enlightening us with your knowledge and also for sharing your findings and opinions with us today on the topic Advances in Traffic Engineering and Management. He gave us an overview of what or we do in these transportation studies like origin and destination study, traffic volume study, and various other studies like incident detection and mitigation. And he enriched us in this session with some speed technologies like multi-target radar systems with the coordinate system and the other challenges that we face during the volume counts, which can be far beyond the capacity of human to analyze all the informations. So we can adopt the artificial intelligence on this traffic data analysis tool for advanced freeway traffic management for the better management. There are some detector technologies also which he discussed like in situ, intrusive and non-intrusive technologies, among which he gave a clear concept on the vein motion systems for the intrusive technologies. Also, I especially like this session where he mentioned about various emerging technologies like the TRAZER, the possibilities of that software were discussed, billboard analytics, and TIRTL software about the TIRTL for the speed detection, red light violation detection, he explained with the statement for the same, and the wireless system, WiTrac for the vehicle actuated traffic signals, and many more technologies, emerging technologies were discussed in this session by him, especially the emergency vehicle signal preemption, where he shared some of his findings about the audio-based vehicle detection and the integration of audio with the video-based vehicle detection and classification. Since there are a lot of challenges while carrying out this collecting of this data, we need this accurate data collection processing by taking the remedial measures, we can overcome this with the help of the emerging technologies. I'm confident that from this session, the participants were able to glean on the vital information about various emerging technologies for data collections in traffic engineering field. Thank you so much, sir, for the informative session. We are really obliged, sir. Thank you.
Thank you, Christy. Thank you, Matthew sir and India. Okay, it has been my pleasure. Thank you very much. Have a nice day.
Thank you, sir.
Thank you, sir. Thank you.
Thank you. Okay, sir. Bye-bye. Can I log off?
Okay, sir.
Okay, sir. Okay. Wish you all the best. My best wishes. Okay. Bye-bye.
Thank you.